Well, howdy, folks. Welcome back to another iteration of COMP40. Today, we're going to start finally getting back into some new content. In the next two lectures, we'll be introducing the Universal Machine Macro Assembler Language, which will be the focus of your last homework assignment. Back to our familiar roadmap, for this final assignment, you will be fulfilling this part of the roadmap. You're going to be implementing an application to run on your emulator. The application is a reverse Polish notation, or RPN calculator. Instead of writing out calculations with the operator in between the operands, like 3 plus 4, an RPN calculator specifies its operands first, then the operator. So instead of writing 3 plus 4, you'd write 3, 4 plus to encode the same addition operation. All of the details about what an RPN calculator is and what it should be doing are in the homework spec, but it's also a real thing in the world, and you can look at Wikipedia if you're interested in what's this reverse Polish notation thing. But what about this part of the roadmap? We haven't built a language processor on the Well, there used to be a build your own language processor assignment long before I was at Tufts. The students would develop an assembler that could take a slightly higher level program than a binary and assemble it into machine instructions to be run on your emulators. That assembler assignment has since been absorbed into this and the next lecture, and a working assembler is provided to you for the last homework. Today, we're going to start going over how to transform the 14 simple instructions into a more interesting macro language. We'll give you this macro language to build your RPN calculator. As a reminder, here are the instructions the can execute. Writing a program that does anything meaningful with just these instructions would be quite a nasty situation to find yourself in. It would be great if we had more instructions, or at least more freedom with how an instruction can be specified to make our programming jobs just a bit easier. And that is the purpose of the Universal Machine Macro Assembler language, also called the UMASM language, or UMASM language. It's not totally clear which letters of UMASM correspond to this text. I like to think the U is for Universal Machine, the M is for macro, and ASM is for assembler. That's a pretty standard abbreviation, ASM for assembly or assembler. This language provides you with a syntax to specify not only the instructions, so you can write what look like lines of code instead of having to write bits in big endian notation. Not only does it give you a new syntax for instructions, but also provides more instructions in the form of macros. For example, you'll have access to more arithmetic operations than the technically provides, each of which is realized as a set of one or more instructions. For example, the UMASM language provides a binary XOR instruction. The doesn't actually know how to do an XOR, but it does know how to do a NAND operation. So the assembler blows out this macro instruction into a set of actual NAND instructions that really perform the computation. If you're not familiar, XOR stands for exclusive OR. It's another bitwise operation like AND, OR, NAND, things like that. And NAND can be used to implement an exclusive OR. This language also provides multi-byte outputs, letting you print out strings and full 32-bit numbers without having to break it down into individual byte operations. For example, this one output instruction will be assembled or blown out into 4 instructions that load each character's ASCII value and output it in turn. So this is the ASCII value for capital H, lowercase I, and then the actual output instruction is applied to those registers. We also get access to non-register operands. You can specify a memory location as an operand, a literal value like a number or character, or the label of another instruction in your UMASM program. For example, this isn't a legal instruction because it has a non-register operand, the immediate value 5. The assembler blows it out into a load value instruction, loading the value of 5 into a register, and then doing an actual addition, which requires 2 registers as its operands. That should still say labels. Forgot to update that. Oh well. We also have more x86-like instructions. Things like push, pop, and a go-to that acts like a jump with some extra baggage. The basic idea of the UMASM language is that it provides a syntax for the instructions you're already aware of, plus some new macro instructions. And these macro instructions correspond to bundles of multiple instructions that are unpacked when the assembler runs. For the rest of this lecture, we're going to talk at a higher level about the assembler and its language. And in the next session, we'll go into a bit more detail about how you can actually build simple things, simple programs with the UMASM language. Let's see first how this picture of compiling a program should be modified to convey what the final assignment entails, to give you sort of a mental model of the process of assembling. You'll effectively be dealing with assembler source in the form of UMASM programs. Those are files specified with a .ums extension. Although we call this an assembler language, a UMS file doesn't really go through a real assembler, which is supposed to simply translate an assembly program into a relocatable object file. Instead, our assembler does both the conversion to machine code and the linking step. So we can have multiple UMS files, pass them to our assembler, and it will both replace the macros with the correct instructions and link the files together into a single final executable. Our linker is called UMASM, Universal Machine Assembler, and it generates a executable. The typical command to perform this assemble and linking operation looks like this. The assembler is invoked with the UMASM command. You can specify the output executable's name, just like with GCC, and then you'll give a series of files written in the macro assembly language to be linked into that final executable. You can then run the resulting program on a emulator. So for your final assignment, you're going to be writing these .ums files to implement an RPN calculator. So here are the major topics for the rest of today and the next lecture. First, we'll go over more of the UMASM language as a whole. Next, we'll talk about some new aspects of assembly that you haven't had to deal with yet directly. In the BOM assignment, you had to read assembly that was a translation of C instructions. But there's other assembly code that makes a program actually run properly. For the UMASM, you're going to have to deal with these other assembly components that correspond to what happens under the hood to set up a program before main starts executing. Some of these components are required to get your resulting executable to work, but many of them are simply used to keep your UMS files modular and organized, which will factor into your S&O grade for this assignment. Finally, in the next lecture, we'll get into a couple examples showing how to program for the with this new macro language. First up, let's just talk a bit more about the UMASM language conceptually. While this is a computer language, it's a notation for computation, it doesn't quite fit into the major categories of language we've been dealing with this semester. The whole point of a computer language is to provide a way for humans to specify a sequence of instructions, typically for a processor like Intel's Core i7 or AMD's A8 to execute. So-called high-level languages let you specify a computational result completely independently of the machine on which the computation will be performed. When we're writing C programs, we aren't thinking about or we aren't writing code that specifically talks about how the processor should execute. We use a compiler or interpreter to translate one high-level statement or instruction into many machine-level instructions. Conversely, assembly languages are completely dependent on the processor. Different processors might have different assembler instructions, and one assembly level statement often gets translated into one machine instruction. There are some exceptions, though, with things like label references, where machine code has no notion of a label. There's not a one-to-one correspondence. The UMASM language doesn't really fit into either of these categories. It's what we call a macro language, which is simply a way of augmenting a pre-existing language with so-called macros. For example, the C preprocessor language augments C with macros, which you have seen before. But what really are macros? Well, they're basically rules that specify how one snippet of text should be transformed into another directly. In other words, a macro captures a direct substitution. Wherever the macro occurs, it will be substituted with some other text. We've seen this notion of a substitution before in the C preprocessor with the #define directive. This one that I've written here defines a macro called pi, that will be replaced with 3.14, this text, wherever the pi occurs in the code following this define statement. So how does macro substitution work in the UMASM? Well, if a line of UMASM code directly corresponds to a UM instruction, this is like the load value instruction, no substitution is done. The UM program generated will simply have that same instruction in place, but encoded in bits. On the other hand, if you have a line of UMASM code that contains a UMASM macro, like XOR, the assembler replaces that one instruction with a set of UM instructions. This is different from compiling one C instruction to many assembly instructions, because a given macro is always just literally replaced with the same set of UM instructions. The only differences are what register names might be substituted in, but no analysis or reordering of instructions are done by the assembler. If there's an instruction here, the resulting substituted instructions will be in the same place. So the UMASM both provides a syntax for our UM instructions and a set of macros that augment those simple instructions. It turns out that all of this syntax can be succinctly presented using a special formalism called a grammar. A grammar basically formalizes this notion of textual substitutions, and we often use them to summarize all the valid syntax for a language. For the UMASM, we will provide you with a grammar that you can use to determine how to construct new instructions and how to ensure syntactic correctness of existing instructions. It's basically like an English grammar. Whereas an English grammar, or a grammar for any other spoken language, says how you can combine chunks of words to form valid sentences, the UMASM grammar says how you can combine chunks of text to form syntactically valid programs. When a compiler throws a syntax error, it has found something that it can't match against with its grammar. So when you see a C syntax error, that's because you've written something that can't be generated from the C language grammar. So before showing you the UMASM grammar, let's first get a bit familiar with just formal grammar notation in a hopefully more comfortable language, English. So here's an English sentence. Joey went to the store. But how do we know that it's valid English? Well, first we use parts of speech to categorize words in a language as things like nouns, verbs, prepositions, proper nouns. And then grammatical rules tell us how we can combine and order these parts of speech in general to form legal sentences. So each of these lines, we call each of these a grammar rule or production. I might use those terms interchangeably. And each of these rules has two major components, separated here by an arrow. So one component's on the left, we call that the left-hand side, and the other component is the right-hand side. They're separated by an arrow. The left-hand side is usually a symbol or name that specifies what a given rule constructs. So this first rule is saying how to construct a full sentence, which is here represented by the symbol S. So S stands for sentence. This rule, because sentence is on the left side, says how to construct a sentence in this English language. The right-hand side is then one or more symbols or names that indicate how to do the construction, how to construct the thing on the left-hand side. So this one says that in order to construct a sentence, according to this grammar, you need to have a noun phrase represented by NP, followed by a verb phrase represented by a VP. So how do we construct one of these things, a noun phrase or a verb phrase? Well, other rules in the grammar tell us. When you see a new symbol, look for a rule that has that symbol on the left-hand side. Oh, here's one. But here's a second one also. And see what is required to construct it by looking at the right-hand side. So here, we have two choices of how to construct a noun phrase by looking for rules with noun phrase on the left-hand side. A noun phrase is either just a proper noun by itself or a determiner followed by a noun. You'll notice that there aren't rules for proper nouns, determiners, and nouns. There's no rule that has that on the left-hand side. That's because these are sort of like, you can think of them as base cases. There's no more rules to follow. These correspond to actual words that you'll just see in the sentence itself. So here we had an example of multiple rules with the same left-hand side. When this happens, you can combine them in your presentation of the grammar. Here I've condensed the grammar and combined those rules. We also had two rules for a verb phrase, so I combined those two using the bar notation. These bars here, the pipe symbol or bar symbol, are separating different possible right-hand sides for the given left-hand side. So I would read this first one as a noun phrase can be constructed by providing either just a proper noun or a determiner followed by a noun. Similarly, a verb phrase can be built by having a verb followed by a PP, whatever that is. It stands for a prepositional phrase, or a verb followed by an adverb. You don't actually write out this symbol in your sentence that you're building to specify, say, a noun phrase or a verb phrase. We would call this a meta symbol because it's used to help present the grammar. It's not an actual symbol corresponding to something that should be written out in a sentence. So given this grammar here, we can use it to check if this full sentence is grammatically valid, given this grammar. We could write a completely different grammar that might not make it valid. It's just up to the grammar that we have. So how can we check this? Well, we can start from the top. We're trying to build a sentence, check if this thing is a valid sentence. So a sentence is only valid if it's a noun phrase followed by a verb phrase. A noun phrase can just be a proper noun, and this sequence of words does start with a proper noun. So we're all set. We've already figured out that we have a noun phrase at the start because we have this proper noun. So now to determine that we have a valid sentence, we have to check if the rest of the sentence, everything that didn't match this noun phrase, Joey, if everything else is part of a valid verb phrase. So went to the store, is that a verb phrase? Well, how can we make a verb phrase? It's either a verb followed by a prepositional phrase or a verb followed by an adverb. We do have a verb, went, and it's unfortunately not followed by an adverb. It's followed by a preposition. So let's see if the rest of our words, to the store, can be used to construct a prepositional phrase. Then we would have a verb followed by a PP, which gives us a VP, which is what we're trying to construct. So a prepositional phrase is a preposition followed, we do have to, that's a preposition, cool, but then it has to be followed by another noun phrase. Well, a determiner followed by a noun is a noun phrase, and we do in fact have a determiner followed by a noun. So that means that we have a noun phrase here, the store, that follows a preposition to, meaning we have a prepositional phrase. So going back, again, we have a prepositional phrase that's following a verb, went, which gives us a valid VP, and we already decided we had a valid NP at the start. So we have just concluded that we do have a valid sentence in a very roundabout way. A grammar can also point out invalid sentences like this one. If we try to follow some set of rules to construct a sentence, we're going to get stuck at some point. There's no rule or combination of rules that will let us construct a sentence where a determiner is followed by a preposition. A determiner can only be followed by a noun. That's the only rule that has anything about a determiner. So this is not a valid sentence. It is not valid syntax according to this grammar. Grammar isn't just limited to spoken languages or written languages that we're familiar with, like English, Arabic, Japanese, Chinese, whatever. You can do the same thing with mathematical statements. How do I know that this is a valid syntax for a math equation? Well, if I'm given a grammar for expressions, I can check the productions to see if I can construct this string of symbols given these grammar rules. Here we have actually a ton of recursive rules. Our base case is a number. A number is an expression, or can be used to construct an expression. But if we already have an expression and put parentheses around it, that itself is another expression. Cool. Two expressions with a plus symbol in the middle is also an expression. So because 8 is a number, that means it's an expression. So we have 8 and 5 are expressions. And if we put them, if we write them with a plus symbol in between them, that gives us a new expression, this whole term. And by this rule, an expression can be another one, a sub-expression in parentheses. So this whole thing is an expression. We could keep on going. Note that these rules don't say anything about what a chunk of syntax means. This doesn't say anything about what does it mean to write an expression with a plus symbol in between two of them. Does it mean addition? We don't know. It's up to some other set of rules to tell us that. These just specify how chunks of text in this language can be structured. As one more example, here are the grammar rules to construct a compound statement or a block in C. A compound statement is simply a statement list surrounded by curly braces. A statement list is either empty. You can, that's what this symbol says. You can write curly braces with nothing in them, and that's valid. Or you can write a statement followed by another statement list, which is either empty or another statement followed by a statement list, so on and so forth. And then we have a bunch of rules of how to build valid statements in C, like the if, an expression in parentheses, and then some other statement, which could be built from these rules. You can use a grammar not only to check valid sentences, but also to generate new ones. For example, based on this grammar, this is a valid sentence. Since it has a noun, Joey, here's one of our available nouns, followed by a verb and another noun. By the same token, Maggie kicks rocks is also valid. And the same thing for Timmy likes Joey. According to this grammar, you can also construct sentences like trees eats Maggie, because that is a noun followed by a verb followed by a noun, which doesn't seem to make sense. But again, the grammar says nothing about meaning, just what chunks of text can go next to each other. Okay, so those are a bunch of grammar examples. Let's take a look at part of the UMASM grammar. Oh my God, what the heck is all of this nonsense? Take a deep breath, and let me guide you through this grammar at a high level. First, the weird symbol here in the middle, 2 colons followed by an equal sign, this symbol is taking the place of the arrows that we saw earlier. So these symbols are being used to separate a left-hand side of a rule from one or more right-hand sides. Any symbol or word that you see in angle brackets, so everything on the left-hand side, and you'll see there's a bunch of instances of that on our right-hand sides, things in angle brackets, those are things that can be constructed using this grammar, like a full program, a single line of UMASM code, an instruction, a binary operator, and so on. The right-hand sides use the bar all over the place to indicate choices. In places like instructions or these operator rules, they separate full choices from another. So a binary operator can either be this symbol or this symbol or this symbol or this word, so on and so forth. Each of these lines separated by a bar is a different way to construct an instruction. In other places, like the program rule, they indicate partial choices. So this is showing that a program can be built from a line that could be followed by a comment or a new line or a semicolon. We also have some new meta symbols here, things that are part of this grammar's presentation, but they're not actually typed in a valid UMASM program. So for example, in the program and line rules, these curly braces mean 0 or more. So a program is 0 or more lines, while a line can optionally start with 0 or more labels, each of which would be followed by a colon. In this line rule, we have another meta symbol. We have these square braces here. Here are big square braces and then nested square braces. And those represent an option. For example, on a line, a label may or may not be followed by an instruction, meaning that you can have a label on a line by itself. An instruction, in turn, may or may not be followed by a using keyword. Notice using doesn't have angle brackets, so it's something that you would actually type. And a using keyword has to be followed by at least one register, but could be followed by 0 or more registers separated by commas. Finally, some of these rules aren't really grammar rules at all, but are more sort of descriptions of how to build something. For example, to construct a comment, you don't type FROM, a hashtag. This is actually a description of how to build a comment. If you write a hashtag or 2 slashes, anything from that symbol to the end of the line in a UMASM program is a comment. As another example, a register is the letter R followed by some decimal number that's represented here with NN. And an identifier, anywhere where you see ident in angle brackets, that's just an identifier that follows the C rules, except you can't use reserved UMASM terms, which aren't shown in this snippet, but are in the full grammar, and you can't use register names as identifier names. So given these two potentially valid lines of UMASM code, how can we check if they're valid statements in the language? Well, we can see if this grammar can describe them. Okay, so let's see if this first line is valid according to the grammar. We're trying to build a line of UMASM code. So let's see, how can we construct a line? Well, a line can be constructed by a single instruction. So how can we build an instruction? We have a bunch of choices, but we just have like one thing on the left and one thing on the right with this colon equal symbol. Here's an example of one thing on the left, one thing on the right. So we have to see if an L value can be used to construct R3, and if an R value can be used to construct 5. Let's look at the L value and R value. Here's 2 rules for those. An L value can be constructed by a reg, and a reg can be constructed by writing out the symbol R followed by a decimal number. We do, in fact, have an R followed by a decimal number, so this left-hand side does correspond to an L value. Okay, does this correspond to an R value? Well, we can construct an R value by constructing a K, and a K can be constructed by either writing out a hex literal like 0xAF2, writing out a decimal literal, or writing out a character literal. The number 5 is a decimal literal, so we have just shown by the sequence of rules that this is a valid line in our UMASM program. The sequence of rules that captures the structure of this line can actually be visualized over here as a tree structure, which we call an abstract syntax tree. So we were trying to see if this chunk of code constructs a valid line And that line was built from an instruction, which was comprised of an L value and an R value. Notice I'm omitting this, the actual text that we would write here. That's what makes this abstract syntax. It's just capturing the general structure. So we built an instruction from an L value and an R value. The L value is realized as a register, which itself is an R followed by some decimal number. The R value was some literal K, which here was represented as a decimal literal instead of a character or hex. Whew, all right. So at this point, I'm going to ask you, pause the video now and see if you can follow a similar process of following rules in this grammar to determine how this second chunk of text, this second line, is in fact a valid line according to our UMASM grammar. Try that out. Okay, I hope you took a moment to do that. This second line captures, we use these rules to build it up, and it uses this second new instruction where we have an L value on the left-hand side, a register name, and on the right-hand side, we have an R value. We already proved, well, we see here that an R value can be a register, a binary operator, like plus, and then another R value, like a literal, a decimal literal, like the number 256. If we look at these two instructions together, they form two lines. Each of them is a line, and a program can be comprised of 0 or more lines. Each of them can have new lines between them. So these two lines with a new line separating them is actually a syntactically valid UMASM program according to this grammar. So this is basically it for general UMASM instructions today. We're going to go into many more examples next time of how we can combine them to do meaningful things. As one final aside, though, before we move on, notice this rule up here of how to construct a label. A label is just an identifier, where an identifier follows the same rules as in C. Just like in the assembly that you read for the bomb, you can label sections of your code in your UMASM programs and then go to them. There's no jump instruction, but there is a go to. You are going to find this extremely useful in your calculator application, and we'll see examples of this next time. Okay, so that's quite a whirlwind intro to the UMASM language as a whole. Feel free to pause the video, take a break, do something else, and then come back. So now let's see some new aspects of assembly that this UMASM language presents. These new aspects all have to deal with a process's memory and the different sections that comprise it. So just as a review of what processes look like in our systems, not in the again, this is laid out contiguously in virtual memory, lowest address 0 down here, highest address up there. And then we have all these different sections that are used for different things, right? We have where all of our code lives. We have things that can be statically allocated before the program runs, heap in the stack, and then any command line arguments and environment variables. Different components of a program, again, this is review, are stored in these different memory sections. In the UMASM, you'll be indicating that different chunks of your code will fall into different distinct sections. And this is how you're going to be organizing your code for a good SNO grade. For example, all of your instructions will be in one section, just as how all the code to be executed in a compiled C program lives in the text section of a process's virtual memory. The assembler will look for these sections to build a final, nicely organized program. In our processes outside of the world, recall that some sections are used just to store data. Either uninitialized space, where we know that we need to allocate some amount, but we don't know what should go there, or pre-initialized space, where we both know how much space we need to allocate and what value should be placed there. So who's in charge of putting this kind of stuff into the appropriate sections. It's not just done automatically. The operating system somehow needs to make space for this string in this specific section, the static initialized section, and then put the actual bits in that space to encode this given string. It turns out that this is also done with assembly instructions. They just happen to be executed before the operating system as it's executing a program, or your processor, before we reach the actual code in the text section. So there is some code that's executed to help set up this section. It's not in the text section because it's not actual code that should be run when the program is running itself. It's part of setting up the program. For example, if you have a string literal like hello world in your C program, it's thought of as read-only data. That string can't be modified. If you run objdump on the resulting object file, you'll actually see that string literal living in the bits comprising this object file as bytes. Here they are, hello world. These string constants are usually in a section named RO data, or row data, which stands for read-only data. You can sometimes actually find these strings hard-coded in your bombs by looking in the RO data sections when you do an objdump. You're essentially going to be doing the same thing in your assignment. You're going to be specifying which section each chunk of your UMASM code belongs to. So while this picture of an x86 process's memory has about 6 sections, 1, 2, 3, 4, 5, 6, in the spec for the assignment, you're going to see that we recommend dividing your RPN calculator's code into 4 sections. Only one of these sections is mandatory for your code to run properly, and the rest are purely for a solid S&O grade. You're welcome to add more sections if you like, or use different names, except for the mandatory one. Okay, so what are these 4 sections? This first one is the mandatory one. You have to have a section somewhere called init. It has to be called init, and there has to be at least one of these sections across all of your UMS files that you link together, but hopefully you'll have them in each one for you to assemble and link together. To specify the location of this section in the UMS code that you're writing, you use this .section indicator. Every line of code that comes after .section init in a file is going to be stored in the init section in the final executable. And that will be the case until if you have another .section somewhere later, that will specify the start of another section. And that will be separate from init. So what's the point of the init section? The instructions in that section are always executed first in the linked executable. These instructions perform all of the bookkeeping and setup required before the program can really start running. For example, your program will probably need to set up like a call stack, which will let you implement jumps and returns like function calls. You'll also need to notify the assembler which registers it can use to help it implement its macros. These notifications are often done in the init section. And you'll also be performing some basic setup, like maybe allocating some space and then storing individual characters in that space. Potentially, those could be in the init section. You're going to eventually also have to jump to some main function to get everything where your actual code should start executing to implement the RPN calculator. And this first jump, the turning over of control to a main function, is also done in init. All right, next up is a text section. Again, you would use the .section indicator to specify this section in your files. Just like in our x86 processes, your UMASM's text segment will hold the actual code corresponding to your RPN calculator running. This is where, for example, a main label that corresponds to the start of your actual program will live. You could have a completely functioning RPN calculator just by putting all of your code in the text section and only using init to just jump to the start of your text section, jumping to some main label. The RPN calculator, will be able to assemble it and run it, but it will for sure lead to a very poor grade for S&O. So make sure that you're using different sections to actually structure things. And remember that other than init, the other ones have no effect on functionality, just organization. The data section should be used to hold any data structures that are needed to make your program run. If you want to be able to jump to a label and then return to where you jumped, you'll need some form of a call stack. The space for this stack can go in this data section. You'll also need a second stack to implement reverse Polish notation. That's what we call a value stack. A lot more details in the spec. This second stack is just a straight up stack data structure that's used to help realize your program's functionality. It is distinct from the call stack that implements jumps and returns at the assembly level. The final suggested section is the row data or read-only data section. This can be used to hold read-only data that will never be changed once the program starts executing, things like jump tables or constants. So again, these section names, other than init, the names are all up to you, and you can add more than 3 if you like. You're going to be writing UMASM instructions, and the first ones that will be executed are those stored in the init section. That's mandatory. Then you're going to be jumping around to different sections as the program is running. You will use labels and section directives to help structure things and keep everything organized. Init is the only section that must be included for the program to actually work. Otherwise, the assembler will choke. So we have all these different memory sections in our UMASM files. Init, text, data. How do they actually get stitched together into a single executable? Well, when you write nice modular 40 programs, you usually have multiple files, and then you use the compiler to combine them into a single executable. In this final assignment, you'll have multiple UMASM programs, which the assembler will piece together into one executable. You need to understand how this process works so you can analyze the layout of your final program. So in this example, I have 2 UMS files, calc and print. Let's say I followed my own recommendation and organized the code using the 4 suggested sections: init, text, data, and read-only data. I labeled 4 sections of my code using those section specifiers in this specific order. It turns out that other files can use the same section labels or different ones, and they can be in any order that you want. So here my print file starts with a data section. I'm just using these colors, then read-only data, then init, then text. You aren't restricted to contiguous sections either. You can totally interleave sections, and that's still valid. Each one of these sections starts with a .section directive, and I have, for example, here I will have .section init 3 different times in my code. Totally fine. The assembler's job, it will make sure that all the code from, say, the text sections scattered around, that they're all next to each other in the final executable, just how the text section is in a contiguous chunk of an x86 process's virtual memory. So let's see how the assembler, this assembler program, actually does this stitching together when you execute it. When you call UMASM, the program wants to construct a fully formed init section first. This is always done by default, and it's why the init section is mandatory across your UMASM files. The order of the files on the command line, it actually affects how UMASM runs. It looks at the first UMS file given on the command line, and in that file, it looks for the first init section it can find. That first init section gets stored at the start of the resulting file. So any lines following .section init in this first file will all basically be pasted here. It then looks for any other init chunks in the same file. There aren't any in this case. So it then moves to the next file, in this case print, looking for more init chunks. And it stores them in the final program in the order seen, in the order that the assembler sees them as it walks from top to bottom. So the first init section in print gets stored next. Then we keep scanning print for more init sections. We found one, so it gets stored next in the file, and then the third init section is appended. Even if inits are scattered across UMS files, as in this example, they will appear right next to each other in the final executable. So when there are no more init sections, what happens next? We go back to the first file and find the next newly named section that wasn't already dealt with. In this example, that's this text section. So the UMASM program now wants to build a text section because it was the next non-init section found in the first file. So now we repeat the process for the text section. We walk down the first file, adding each text section we see to the executable, then go through the next UMS file, adding each text section found as we walk over the file from top to bottom. This process will then be repeated for each subsequent section seen. In this case, we just have two other kinds, data and read-only data, that are in that order because that's the order that they're seen in the first file. So to summarize all this memory section stuff, there has to be an init section for the UMASM program to run correctly, and the order of code execution in your final executable is dictated by how the UMASM program builds the memory sections in this file. That in turn is determined by how you structure and organize your code into different sections across multiple files. Okay, just one last thing, 2 slides to talk about today, and it's related to these .section things. Those aren't actual instructions, but they're instead somehow telling the assembler some meta information. We call these things UMASM directives. They're basically like instructions to the assembler itself, as opposed to instructions for the This first one we've already seen, the .section directive, and it's used to organize your code, and you can create them as you wish, but you need that init one. Next directive is called space, and it's just written as .space with a number following it, some decimal literal. This directive says to make space for that many 32-bit words, and it initializes them all to 0. This is basically the same thing as what gets stored in the static uninitialized section of an x86 process. That's what you can use this directive to do. We can use it to make space for jump tables, maybe make space for an empty call stack to be used, or constants like this string here. For example, here I'm using it, I'm creating a read-only data section, and in that section, I'm making space for 14 words, and each of which will store a single character. And then in the init section, I'll specify some instructions to be executed before the program really starts to actually store those characters in the space I just blocked off and labeled my string. So I used a label to show here is enough space for 14 words, and I'm labeling it my string. So I can store, if I store that label in a register, I'm basically storing the address of the start of that space. And then I can use that address, I can access a memory segment and store the first character of my string there, store the next address in R3, move to the next character, store the space, and so on and so forth. Here I'm assuming that register 0 has the number 0 in it, because whenever you use the .space directive, the space is always blocked off in segment 0. Okay, there are 3 more directives. The data directive takes some literal, can be a decimal, a hex, or a character, and it just stores that literal in a segment 0. The temps directive tells the assembler which registers can be used to help execute a macro instruction. You can specify 1 or more registers as temps. We're going to see a lot more examples of this next time. And finally, the 0 directive specifies 1 register that should always hold the value 0. This last one sort of acts like a promise to the assembler and helps it issue instructions that need to access segment 0 all the time. We're going to cover these a lot more in detail next time. Okay, so that's it for today. Next time, we're going to see how to actually write programs using UMASM code. This is a lot of new stuff, I realize that. Take some time, review your notes, And once the homework spec is released, use that and some of the other materials provided to help shore up any issues you have with your learning. And of course, I hope to see you at the Q&A session so I can help answer any questions you might have. Thanks so much, and see you next time.